Hello guys, welcome to this presentation on medical applications of multimodal machine learning. First of all, let's start with single model machine learning. I'm pretty sure that you're familiar with different machine learning and deep learning models like convolutional neural networks, CNNs, or recurrent neural networks, RNNs. And you know that these architectures are specifically designed to handle a single kind of modality. Okay, for example, CNNs are designed to handle images, or RNNs are designed to handle text as input. All right, but the thing is that in many domains like healthcare and medicine, there are more than one type of data, more than one modalities that are important for making decisions. Okay, for example, in the healthcare domain, when you go to a doctor, the doctor will take your demographic data, which usually comes in the format of text. He or she will also ask you to do some medical scanning, for example, to do a MRI or CT scan, which comes in the format of image. And also, the doctor may also send you to a laboratory to do some laboratory assessment and bring him the report of that laboratory, which is again in the format of text. So it is very important to uh, you know have a machine learning or a deep learning model that is able to handle all of these different modalities, the text, the images, and the tabular data or different other kind of modalities at the same time simultaneously, like the doctor does. For example, here we see an I believe X-ray scan of chest, which accompanies the final report of what a doctor has written. And for example, if we want to do some prediction task on these reports, is very important for us to take both the image and the text into consideration to have a successful and effective prediction, right? So this is the idea that gave birth to multimodal machine learning, which is basically a kind of machine learning or a deep learning model that is able to handle more than one modalities at the same time. Okay, for example, in this image we have three modalities, which can be text, image, tabular data, voice, I don't know, some sensory data from robots, and all other different modalities and different types of data that we have in the world of machine learning and deep learning, and process them at the same time simultaneously. Okay, the multimodal machine learning is taking all of these modalities as input at the same time. Okay, and it is useful to do prediction or to generate something new or these kind of tasks. Okay, in multimodal machine learning, we are usually dealing with these six areas of challenges. The process starts with representation. It is very important to represent each of the modalities in a way that the machine learning or deep learning model is able to process them effectively and efficiently in future. Okay, we need to find a kind of representation that express the data and the mutual patterns and connections that are available in that specific modality, which is shared with other modalities at the same time. Okay, so we need to find a clever way of representing different modalities. This is called representation. After that, we have represented our different modalities. It is important to do alignment. Okay, what alignment does is basically find the connection between different parts of different modalities. For example, if we have image as a modality and also a text as a modality, the image, of course, contains a bunch of objects, and the text contains a bunch of tokens, or we can say words. What alignments does is that it finds the connection between the different objects of that image and the different words of that text. Okay, this is what alignment means. After alignment, we have reasoning. In what reasoning does is, the most famous task is, of course, to do prediction, to predict, for example, a disease. We can also do generation. Generation means using generative AI features to generate something new. We can also do transference, which means to transfer the knowledge and the information available in one modality into another modality. And of course, at last, we can do some quantification. Quantification means to quantifically uh, assess the performance of the model, and these whole uh, areas that we have done. Okay, this is what quantification means. Yeah, now let's go through each of these areas one by one. Let's start with representation. For example, if you want to represent an image, the very famous way of encoding an image or representing an image is to use CNNs, or convolutional neural networks, which what it does is that it have a bunch of convolution and max pooling, or average pooling, or different kind of pooling uh, layers. And after these layers, we usually have some fully connected layers, and at the end we will end up with an encoding or representation of that image. Okay, for example, in this picture we see I believe it is a VGG16 model, a VGG16 CNN model, which is used to represent this brain MRI uh, image. Another more clever and more efficient way of more effective way of representing images is to use a vision transformer, or a VIT. What vision transformer does is that it takes the image, split it into a bunch of patches, as we can see in the bottom of this picture. And after that, we have split the image into a bunch of patches. We flatten them into a vector format, and we pass that vector format through a linear projection layer. And after that, we add positional embedding to them. What positional embedding does is that it basically gives the model an idea of the order of the patches in the image. Okay, for example, of course, it is important for us to know which patch comes first, which patch comes next, and so on and so forth, and which patch comes at the end. Okay, positional embedding gives the transformer the ability to differentiate the order of different patches. Okay, and of course, after that, these vectors are passed through the encoder part of the transformer. If you're familiar with the transformer architecture, you know that the transformer architecture contains two different parts, the encoder and the decoder. But what is more important for us is the encoder section in the vision transformer. Okay. Yeah, so this was vision transformer. In the encoder part of vision transformers, or any kind of transformer, the most important idea is called self-attention mechanism. What self-attention mechanism does is it is a very clever way of finding the relationship between different tokens or different patches. Uh, what it does is that basically it have three matrices: the query matrix, the value matrix, and the key matrix. And what it does is that in this matrix, it's dedicate to each of the tokens, or each of the patches, a single vector of query key value. And the self-attention mechanism, by dot producting the query value of the current token with all of the key values of other tokens, and then putting it through a softmax function, is able to find the attention weights. Okay, attention weights basically tells the model that for this current specific token, which other tokens are most important, okay, which other tokens are most attending to it, okay, and then it multiplies the result to the value vector and sum it up and give us the output. Okay, this is basically the self-attention mechanism. If we have multiple of these self-attention mechanism working in parallel, we call them multi-head attention mechanism or multi-head transformers. Okay, so this is what multi-head transformer means. All right, so now let's move to token representation. For token representation, we use something called word embedding. Word embedding means that this is a very clever way of representing words or tokens. What it does is that basically maps each word into a embedding space. And what is important about this embedding space is that the distance between different tokens or different words are meaningful. Okay, for example, here we see that this word embedding model was able to put organs which are represented in green color together, and the name of some diseases in the middle which are presented by red together, and also other tasks like these different areas of physician uh, together in blue. Okay, so the word embedding model was able to map these words into a space, into a vector in this embedding space, that the distance between them have meaning. Okay, this is what word embedding does basically. Okay, so for representing a text, we are going to, for example, use RNNs. By RNNs, it also includes GRUs and LSTMs. What they do is that they basically take your sentences, which contains of a bunch of tokens, sequentially, one by one after another, and then gives you a encoded token, I'm sorry, an encoded representation which contains the whole sentence in it. Okay, for example, here we started with a startup sentence token. We put the words one by one, the tokens one by one inside the RNN model, which can be LSTM or GRU, and also at the end we end up with a end of sentence token, and the model was able to, encode all of this sentence and all of these tokens into a single vector here. Also, we can use again transformers for text representation. A very famous transformer model is BERT, uh, which what BERT does is that, of course, we have two phases. The first phase is pre-training, and the next phase is fine-tuning. In pre-training, what we do to train BERT is that we input the tokens of two sentences. Okay, and we expect the bird to be able to perform two tasks. The first task is called NSP, or next sentence predicting, which means that it is basically a binary class classification. We are asking the bird model to predict if these two inputted sentences are related to each other or not. Okay, this is what the NSP output tells us. It is basically one or zero, meaning that these sentences are related to each other or not. Okay. Also, another thing that BERT model we expect the BERT model to do in the pre-training phase is masked language modeling. What this means that it means that we take out a bunch of tokens, usually 15% of the tokens of the sentences, and we expect the BERT model to be able to correctly predict the tokens that are being taken out. Okay, and by performing these two tasks, the masked language modeling and next sentence prediction, we somehow enforce the BERT model to learn the language. Okay, and now that in the pre-training phase, the BERT has learned the language, we will fine tune it for our own specific task. Okay, for example, for medical text representation, we have a fine-tuned version of BERT called BioBERT, which is trained on large corpuses of biomedical sentences. Okay. Yeah, also a very quick note on fusion. Fusion means combining the different information of different modalities. We have two kind of fusion. The first one is early fusion, and we also have late fusion. Early fusion means that we, combine the information of, the representation of different modalities before making a prediction. But late fusion means basically uh, do this combining thing after making a prediction. Okay, as you can see in this chart, it is very obvious what the difference between early and late fusion is. Also, we have in this slide we can see the some fusion techniques, which is gives us the representation of combination of two or more modalities. For example, here we have in these two vectors we have the unimodal representation, which is basically the representation vector multiplied by some weight. Also, we have here what we have is the bimodal fusion, which is the outer product of these two different modalities, again multiplied by some weight, and this gives us a very comprehensive fusion of different modalities. In the bottom, you can see the fusion of three modalities, which these green beans are the unimodal uh, representation. These light blue color are the bimodal representation, and in the middle we have trimodal, which is the outer product of uh, these three modalities, which gives us some this 3D shape. All right, so this was representation. Now let's move to alignment. Alignment means, as I explained, aerial is means that now that we have two representation, we need to find the connection between different parts of these representation. Okay, for example, if we have an image and we have a text, we must somehow relate different parts of these two modalities together. Okay, for example, here we see that the model was able to align these green sentences with this section of the image, or for example, this red last sentence with this left hand side of this image. Okay, this is what alignment is. Or for example, here we can see, I believe this is an image captioning task. And when the text was talking about the woman, the model attended to the people available in this image. As you can see, the model sees these parts. And when the sentence was talking about the frisbee, the model was able to attend to the frisbee, the toy here. And this is what basically this is the miracle of alignment. Okay, for doing alignment, we are going to use something called cross attention mechanism. We are already familiar with self attention mechanism. Cross attention mechanism is basically the same. The only difference is that in cross attention mechanism we have two modalities. For example, we have modality alpha and modality beta. And what cross attention mechanism does is that again we have the set of our query key and vector. But the difference between cross attention mechanism and self attention mechanism is that in cross attention mechanism, we dedicate the query uh, tensor to one of the modalities and the key and value tensors to another modality. Okay, and by this way, the cross attention mechanism is able to find the relationship, the attention between these two modalities, how modality beta is attending to modality alpha. Okay, this is basically what alignments does, what we need in alignment, right? And we can achieve that by the help of cross attention mechanism. All right, so here we see the Wilbert, which is a very famous multimodal uh, machine learning model. Uh, and it has, we here see a image containing a bunch of objects and also a sentence containing a bunch of tokens. And what we see is that the model was first the model first embedded these two representation, and then it has two cross-model transformer modules. Okay, we have two cross-model transformer modules because we want to find the you know we need to find how the tokens of the sentence is attending to the objects of the image and vice versa. Okay, we also need to know how the objects of the images are attending to the tokens of the text. So this is how this is why we are having two cross-model transformer modules, and after that we also put a unimodal transformer and got the representation at the end. Another famous model is WILT or VILT. Uh, it is again a multi-model working with vision and language at the same time. We can see the image was splitted into a bunch of patches, like the vision transformer architecture. Also, we have the sentence, which is splitted into a bunch of tokens and pass-through word embedding, which I previously explained to you. Then we have added the uh, model type embedding and position embedding and patch position embedding to these tokens and patches, and then it was passed through a transformer encoder. And what we expect this transformer encoder to be able to do is to first do image text matching, which is the idea somehow taken from BERT, which image text matching basically is again a binary class classification and mentions if this sentence is related to this image or not. Okay, this is what image text matching does. Another thing that this architecture does is masked language modeling, which means again we take out a bunch of sections of the sentence, and we expect the model to be able to correctly predict which tokens, what tokens we have taken out of the sentence. Okay, so this is how WILT works. All right, and we also after that we have represented and aligned the different modalities in our multimodal or in our multimodal machine learning or deep learning model. We also need to do some reasoning or generation. So I have listed a bunch of tasks that are currently being actively researched in computer science, and specifically in the medical applications and healthcare applications of computer science, uh, using multimodal machine learning. For example, the most simple thing that we can do is a multimodal diagnosis. For example, here we have a bunch of clinical data in the form of text, I believe, which was passed through a denoising autoencoder. We also had some X-ray images, which were passed through a bunch of convolutional layers, and then we have aligned these two representation using this cross-model transformer, and then we use a sigmoid function to do the diagnosis prediction. Okay. Also, this is very important for some diseases that are progressive. They progress through time. For example, Alzheimer's, some kind of cancers, or some schizophrenia, I believe. And if we are able to use multimodal machine learning to detect and diagnose these diseases in their earliest stages, it would be a great help to the both to the doctors and to the patient to treat this disease effectively. Okay. The next multimodal machine learning model is CLIP, which basically what it does is again it has the word embedding idea in its head, and what it does that is that it has a text and an image, and it encode these two different modalities into a same shared space, and we are able to search in this space and retrieve similar images or retrieve similar passages. uh, by finding the closest matches through an algorithm like KNN. All right, so this is what Clip actually does. Clip was a model, I believe, developed by OpenAI, and this is what it does. It's map the texts and the images into a same shared space, and it hopes to put similar texts and images together, closer together, and different shapes different text and images far from each other. Okay, this is what Clip does. Also, we have medical report generation, which is basically image captioning. We give the model an image, and we expect the model to write a report for us, to write a report, a bunch of sentence, output a caption for that image, which in our case is a medical report. This is what image captioning in medical images look like. We also have medical visual question answering, which means that we have a image and also we have a question. Of course, this is multimodal because we have two different modalities. The image is, of course, image, and the question is text. So the model must be able to process these two different modalities at the same time and understand the question, and be able to align it with the image representation. For example, in this image, the user asked what kind of image it is, and the model was able to successfully output CTA. Okay, this is what medical visual question answering means. Also, we have multimodal medical image retrieval, which means that the we have a bunch of paired images and descriptions as text, and we need to develop a multimodal uh, machine learning model that is able to successfully retrieve similar images and similar text for the user. The next research project that I have brought is called language guided medical image segmentation, which again is, of course, multimodal. We have an image, in this case, it's I mean, an MRI, and we need to do segmentation on these images. Okay, but what is important for us is that this segmentation, we need a language, we need it to be language guided. Okay, so in addition to the image, we have also provided a text, and we expect the model to be able to segment the image in a way that is directed and instructed in the text. Okay, so this is what language guided medical image segmentation means. For example, in this chest X-ray, the user mentioned that he wants the right lung and the unilateral pulmonary infection, and the model was successfully able to uh, only segment the right lung for the user. Yeah, so this was the presentation on multimodal uh, machine learning applications in medical and healthcare domain. I hope you have enjoyed this presentation, and thank you very much for your attention.